Hello guys, welcome back. This is lecture 16 of the lecture series Signals and Systems. In this video, we will study about the representation of discrete time signals in terms of impulses, and we'll also see how to represent discrete time LTI systems using impulses, which will then take the form called as the convolution sum. And then we'll look at the properties of LTI system, and finally we will end our lecture with discussion about linear constant coefficient difference equation. So let's get started. So first let us look at the representation of discrete time signals using impulses. So this one we already looked at in the continuous time domain. In the discrete time domain, it is very easy to visualize. So if you have any signal x of n, let's say you have this. So this is the signal x of n, and let's say it has some value 1, 2, 0.5, 1, 0.5, 1, okay? So now we have to represent this x of n using impulses. So how does the impulse look like? So represented by delta of n. And in discrete time, we have finite value with value 1 for the unit impulse, right? So what about the shifted impulses? So if I have delta of n minus 2, so I'll have it at 0, this at 0, 1, 2. I'll have only here, right? All other places, it is going to be 0. So here it is 1. And everywhere else it is going to be 0. So what I can do, I can write x of n as sum of, okay, let me first write it as, I'll see at x of 0 into delta of n plus x of 1 into delta of n minus 1 plus x of 2 into delta of n minus 2 and so on. I can write it this way, right? So these deltas are nothing but they will have unit values, like delta of n will be 1 only at 0 and everywhere else it is going to be 0. So when I take x of 0 and multiply it with this, I'll get this one, x of 0 here, right? And what will this look like? It will have x of 1 value at 1, right? And everywhere else it will be 0. And this also will be 0 everywhere. And once I add this all up, what will I get? I should get back the entire signal x of n. So that is what I have written on the left hand side. So I'll have x of 0, x of 1, x of 2, and this side I'll have x of minus 1, x of minus 2, right? And depending on whatever the value, it will be equal to 2. Here it is. So I have to write another x of 1. This is x of 2, x of 3, right? So here it is 1, then 2, then 0.5, then 0. This side it is 0.5 and 0 and so on, right? So I can write it in this form. And how do I write it as a summation? So if you observe, you have summation x of k, because this is the variable running, changing 0, 1, 2 and so on. Delta of, you have n minus, again here you have the changing variable. So I'll have n minus k. And k runs from minus infinity to infinity. So this is your representation of x of n in terms of impulses. Okay. Again, if you see, this is nothing but the shifting property. So what it means, from the x of n, this delta samples each value at x of n, right? So your delta of n samples the value at x of 0, delta of n minus 1 samples the value at x of 1 and so on. And if we add them all up, we get x of n back. So as a simple example, you can take the unit step function u of n. So if you substitute in this, you'll get u of k into delta of n minus k. And u of k is equal to 1 for k greater than or equal to 0, right? So your summation will only be non-zero from 0 to infinity, and you will have u of k is 1, so delta of n minus k. So this is also your unit step function in terms of the impulse. So what you will have at k equal to 0, it is just delta of n, and k equal to 1, it will be delta of n minus 1. So if you add all of them up, you will get the unit step function. Okay. Now let us see what happens when we pass this into a system. So system output in terms of impulse response. And in general, we are discussing about LTI systems. Okay. So this one is valid for any signal because we haven't entered the signal yet, system properties yet. So now only we are imposing the constraint that it is LTI system. So let us look at what happens. So I have my x of n equal to summation k equal to minus infinity to infinity x of k delta of n minus k. So if I pass it through a system which is linear, what will happen? So I'll get some output y of n. So since it is linear, if my delta of n minus k gives a response, impulse response such that it is hk of n, I am giving k here to represent this k, because the impulse response will depend both on n and k, because the system is only linear. We haven't said anything about the time. Okay. So then your x of k into delta of n minus k, where x of k is going to be a constant. So this will give me x of k into hk of n. And if I sum it up, even in the output, it will be sum, right? So I'll get summation k equal to minus infinity to infinity x of k hk of n. So this is what I'll get for a linear system. Now if I also impose the constraint of time invariance, then what will happen? So I'll take the same input. I will say my system is linear and time invariant. So what it means, if delta of n gives me h0 of n, then my delta of n minus 1 should give me h0 of n minus 1. Delta of n minus k in general should give me h0 of n minus k. And we can just drop this 0 and just consider h of n minus 1 and h of n minus k. Then what will happen to my output? It will be summation k equal to minus infinity to infinity x of k h of n minus k, right? Because this is what will be your impulse response, right? This is your impulse response. So why we are calling it as impulse response? Because it is the response of the system for unit impulse, right? So it is called as the impulse response. And this itself is called as the convolution sum. So in the continuous time domain, we would have discussed about the convolution integral, where you will have this integral x of tau, h of t minus tau, d tau, right? So now here it is just the sum. So let us see an example to visualize what happens. Example. So let's say we have our x of n given by this graph. So it is at 0 it is equal to 2, and at 1 it is 0.5, and everywhere else it is 0. Okay. And let us take our h of n to be 1, 1, 1 for 0, 1, 2, and everywhere else it is 0. Okay. So now I want to calculate y of n. So my y of n is nothing but summation k equal to minus infinity to infinity x of k h of n minus k. But you know your x of k is non-zero only for 0 and 1. So you will get x of 0 h of n plus x of 1 h of n minus 1. So this is nothing but 2 into h of n plus 0.5 into h of n minus 1. So you can calculate by finding h of n, then multiplying it by 2, and finding h of n minus 1, multiplying it with 0.5, and then adding them up. So let us try that. So h of n is already there. 2h of n will just be 2, 2, 2, right? 0, 1, 2. And your h of n minus 1 is nothing but right shifting this by 1. So it will be this. So 0, 1, 2, 3. And its values, if I say 0.5, these will be 0.5. Now if you have to add them, what will I get? I should get y of n. And if you see at 0, there is only this 2h of n. So I'll get a value of 2. And at 1, what do I have? I have 2 plus 0.5. So 2.5. At 2 also I have 2 plus 0.5. 2.5. And at 3 I have 0.5, right? And 4 I have nothing. So it is 0 everywhere else. Okay. So this is one way to calculate y of n. But if your x of k is actually infinitely long, then you can't find infinite times of h of n and then keep adding them all up, right? So we have another method. So in that what we have is, so to find y at a particular value of n, what we do is, we take x of k and multiply it with h of n minus k, right? We first perform the multiplication and then we sum it all up. So that will give me a particular value at n, right? For example, if I want to find y of 0, I do it by first taking the product of x of k and h of minus k, right? And then summing it from minus infinity to infinity. Similarly, my y of 1 will be, you just need to shift this by 1, right? So x of k, h of 1 minus k. This is nothing but right shifting h of minus k by 1 unit, and then you again sum it up. So let us see how it happens. So we'll take the same example. So first what we have to do, find h of n minus k. Here k is the variable. Why k is the variable? Because we are going to sum it up from k equal to minus infinity to infinity. So you have, let's say, h of k first. It's nothing but 1, 1, 1, 0, 1, 2, which is k. And h of minus k, how will it look? It's just a reflection about the y-axis. So it is 0, minus 1, minus 2, 1, 1, 1. And how my h of n minus k will look? It is just right shifting by n units. So 1, 1, 1, this is k. This will be n minus 2, n minus 1, and n, correct? And next what I should do? Multiply x of k and h of n minus k. Okay. And what I have to do? Keep shifting n and find y of n for each n. Okay. So let me also plot here the x of k. As you know, it is 2 and 0.5. 2 and 0.5. And this is 0 and 1. And my h of n minus k is nothing but 1, 1, 1, n minus 2, n minus 1, n. And my y of n is summation k equal to minus infinity to infinity x of k h of n minus k. So if you observe, when there is a overlap, if n minus 2 is greater than 1, then my y of n is going to be 0 because there is no overlap between these two signals, right? So when it happens, when n is greater than 3, my y of n is going to be equal to 0. So is it matching with our previous result? Correct, right? When n is greater than 3, from 4 onwards, it is going to be 0. Yes. So then, again, when we shift it to the left side, right? When n is negative, what happens? For n less than 0, correct? Again, my y of n is going to be equal to 0 because there is going to be no overlap between these two signals. Again, this you can check it from here. For n less than 0, it is again going to be 0. So now what happens when n equal to, between these, so non-zero, y is non-zero for n equal to 0, 1 and 2. So for each of these you can check. So for n equal to 0, what happens? So your h of minus k, how will it look like? So you have to just substitute 0 here. Minus 2, minus 1, 0. So it will have 1, 1, 1. So this you have to multiply with h of k. And what you will remain is only this 2. Right? When you sum it up, again you will get 2 only. So x of k into h of minus k will be just this 2. So your y of 0 is equal to 2. And n equal to 1. Let's see what happens. So this h of minus k will just shift one more unit. So your x of k into h of minus k will be this plus this. So 2 and 0.5. When I sum it up, I will get y of 1 equal to 2, 2.5, right? And at n equal to 2, what happens? So your h of minus k will actually start from origin and will have these 3. So again it will overlap with this 2 and 0.5. So I'll have 2 and 0.5. So again my y of 2 is equal to 2.5, right? And for n greater than 3 only it is 0. So it is not 0 for n equal to 3 also. So for n equal to 3, what happens? So your h of my n minus k starts from 3 minus 2, 1. So 1, 2 and 3. So only this 0.5 will remain. So my y of 3 will be 0.5. So once you find this, you can plot. So you have 2, 2.5, 2.5, 0.5 and 0. So 0, 1, 2, 3. This will be your y of n. Okay. So this one you can also obtain for if x of k is infinitely long also, because you will have some form of convergence in this summation term. So you can easily find it out. So let us see an example for that. So it's my example 2. So let's say my x of n is alpha power n u of n. Of course, we can say alpha is less than 1. And let's also say it is a positive number. Okay. And my h of n is nothing but u of n. So how will my signals look like? My x of n will look like this. So it will start from 1, and then it will keep reducing 0, 1, 2, 3, 4 and so on. This is n, and my h of n is the simple step, unit step, right? It is going to be 1 for n greater than 0. And for n less than 0, both are going to be 0. So to find my y of n, again the convolution is denoted by this symbol. You already know that. So I have to write k equal to minus infinity to infinity x of k h of n minus k. Okay. So my x of k will remain same as x of n. Only the variable will change to k. What happens to my h of n minus k? I have to reflect this about the y-axis and then shift it by n units to the right. So how will it look like? So it's having a right tail now, it will come to a left tail. So I'll be having something like this. And where will it start from? It will start from n, right? Because when I reflect it, I'll get h of minus k, and then I have to push right by n units to get h of n minus k. So this will be n minus 1, n minus 2, and so on. So all will have a value of 1. So this is k. Now I have to multiply these both and find y of n. So before that, I have to observe that for what value of y of n is this 0 or non-zero. So if my n is going to be less than 0, then there is no overlap between x of k and h of n minus k. So my y of n is going to be equal to 0. And for n greater than 0, there will be overlap, right? For greater than or equal to 0. So until what is the region of overlap? Region of overlap. Of course, for k less than 0, it is going to be 0. So your k is greater than 0 and less than or equal to n, right? Again, at 0 also there is overlap. So it is greater than or equal to 0 and less than or equal to n. So how will my summation look like? Summation k equal to 0 to n x of k h of n minus k. So now I have the expression for x of k and h of n minus k also. I know it is going to be 1 everywhere, right? In this region. So I can write the sum of k equal to 0 to n. X of k is alpha power k, right? And it is anyway going to be scale alpha power k, u of k. U of k only we have taken care by restricting this region. And your h of n minus k is going to be 1. So now it is just the summation of k equal to 0 to n alpha power k. So it is just the geometric progression sum. So we'll get 1 minus alpha power n plus 1 by 1 minus alpha. So this is for n greater than or equal to 0. So what will be your y of n? It will be 1 minus alpha power n plus 1 by 1 minus alpha into u of n. Because it is equal to 0 for n less than 0. Okay. This is how you solve these type of questions. So to summarize this, we saw the convolution sum, which is given by x of n convolved with h of n is nothing but summation k equal to minus infinity to infinity x of k h of n minus k. So now let us look at the properties of this convolution sum. So my first property will be the commutative property. So what it means? X of n convolved with h of n is equal to h of n convolved with x of n. So what is the difference in these both? This will give me summation k equal to minus infinity to infinity x of k h of n minus k, and this is going to give me summation k equal to minus infinity to infinity h of k x of n minus k. So let us prove this. So just simply proved by change of variables. So let me say call a new variable r is equal to n minus k. Then what happens to k? K is equal to n minus r. And what happens to my summation? So k equal to infinity means n is equal to minus infinity, and k is equal to minus infinity means n is equal to infinity. So my summation is going to go from r equal to, this is r, right? So infinity to minus infinity, and what I have, x of k is going to become n minus r, and h of n minus k is nothing but r. So but my summation, it doesn't matter if I add it from first to last or last to first. So I can write it as r equal to minus infinity to infinity x of n minus r into h of r. So now I can replace r with k again. Just change of variables. So it doesn't matter because it is under the summation. So minus infinity to infinity. I'll take h first. So h of k x of n minus k. So this is what we wanted to prove, and here is the proof. Okay. And my second property will be the distributive property. So it states that x of n convolved with h1 of n plus h2 of n is equal to x of n convolved with h1 of n plus x of n convolved with h2 of n. So here the convolution is getting distributed over addition. So if you want to visualize it in terms of system, this is nothing but x of n, you're passing through h1 of n plus h2 of n, and you're getting some y of n. And this is nothing but you're taking x of n and you're passing it through two systems. One is h1 of n, other is h2 of n. So these are LTI systems, and these h1 of n, h2 of n are nothing but the impulse response of these systems. So and then finally you're adding these both, and you're getting y of n. So it states that both these are equal. What does the commutative property state? If you have x of n passing through a system with impulse response h of n, you get the same output as your h of n passing through the system with impulse response x of n. Right? And distributive property states this. And proof is straightforward from the definition. So you have y of n equal to, so x of n convolved with h1 of n plus h2 of n. So this is nothing but summation k equal to minus infinity to infinity x of k into h1 of n minus k plus h2 of n minus k. And this is gonna give me k equal to minus infinity to infinity x of k h1 of n minus k plus summation k equal to minus infinity to infinity x of k into h2 of n minus k. So I'm just taking the multiplication inside and then separating the summations. So this is nothing but your x of n convolved with h1 of n plus this is nothing but your x of n convolved with h2 of n. So this is the distributive property. So next let us look at the associative property. So what does the associative property say? So x of n convolved with h1 of n convolved with h2 of n is equal to x of n convolved with h1 of n, and then you're taking this result and convolving it with h2 of n. So what it translates in the system block diagram, so this will be nothing but you're passing x of n through a system with impulse response given by h1 of n convolved with h2 of n, right, and y of n. And what this gives, you first pass x of n through a system with impulse response h1 of n, and the result you pass through another system with impulse response h2 of n, and you get the same output y of n. So this proof is little involved, so let us try to derive. So let us start with the RHS. So what we have, x of n convolved with h1 of n convolved with h2 of n. So first let us find this one. Let's call it y1 of n equal to x of n convolved with h1 of n. Okay. So what will this give me? I'll assume a variable first k, let's say. So k equal to minus infinity to infinity, x of k, h1 of n minus k. So this will be my y1 of n. So then this is equal to y1 of n convolved with h2 of n. So this again I have to use a different variable, so I'll use r. So minus infinity to infinity, y1 of r, h2 of n minus r. So what I will have here, summation r equal to minus infinity to infinity. If I substitute y1 of r, then I have to replace n with r here. Summation k equal to minus infinity to infinity, x of k, h1 of r minus k, h2 of n minus r. So now to get h1 of n convolved with h2 of n, I have to first sum over r and then take the k. So what I'll do, I'll take all the k terms like this. So I have x of k, and then I'll do the r summation first. So I have h1 of r minus k, h2 of n minus r. So if you observe, to bring it to the form of h1 of n convolved with h2 of n, this is of the form k equal to minus infinity to infinity, h1 of k, h2 of n minus k, right? So my h1 should have only one variable here. So I have to replace my r minus k with some other variable, let's say call it t. So if I do that, what happens to my summation? It's still going from minus infinity to infinity, right? And then what happens to my r? R minus k becomes 1, and r is nothing but t plus k, right? So I will get summation k equal to minus infinity to infinity, x of k, summation r equal to, I replaced it with t, so t equal to minus infinity to infinity, h1 of r minus k is nothing but t, and h2 of n minus r, r is nothing but t plus k. So I'll get n minus t minus k, right? And I can write it as n minus k minus t. So if I call my y2 of n as h1 of n convolved with h2 of n, and let me write it as summation t equal to minus infinity to infinity, h1 of k, h2 of n minus k, so this t. Then what is this looking like? It is looking like n replaced with n minus k. So this is nothing but y2 of n minus k. So this is going to be, my RHS is going to be summation k equal to minus infinity to infinity, x of n, y2 of n minus k. So now this is nothing but my x of n convolved with y2 of n, right? And my y2 of n is nothing but h1 of n convolved with h2 of n. So, and this is nothing but my LHS. So I prove that LHS equal to RHS. So this is the proof. Okay. So our convolution property satisfies commutative property, distributive property, and associative property. So now let us look at the properties of LTI systems using this impulse response function. Okay. So properties of LTI system based on the convolution sum. Or we can also say the impulse response given by h of n. Okay. So the first property we'll see is memoryless. So what does memoryless means? Your y of n should depend only on x of n. So if I write y of n as x of n convolved with h of n, and for convenience I'll use the commutative property and write it this way. So what will my y of n be? It will be summation k equal to minus infinity to infinity h of k x of n minus k. So if you see, only at h of k should be not equal to 0 for k not equal to 0. Then only all the terms like x of n minus 1, n minus 2, everything, n plus 1, n plus 2, everything will be 0. So which also means that h of k should be non-zero only for k equal to 0. So which means h of k is of the form some delta of n, and it can have some weight given by some complex number k. So this will be my form of h of n. So this, if the LTI system should be memoryless, then its impulse function should be of the form of k delta of n, right? And again you can observe that your if y of n, or let's say your x of n convolved with delta of n is nothing but, you just need to replace this with delta of n. So it will give you x of n itself. And if you have a factor k, here also will have a factor k. So this is again a special property of the unit impulse function. So next, let us see the invertibility property. And again, this is only valid for LTI systems, right? Because this definition is valid only for LTI systems. Okay, coming to invertibility, what we have? So if you have x of n passing through some system with impulse response h1 of n, then if it has an inverse, let's call it h2 of n, then it should give me the same output x of n itself. So h1 of n and h2 of n are inverse of each other. So what it means, my x of n convolved with h1 of n and then convolving it with h2 of n should give me x of n back. So using associative property, I have x of n convolved with h1 of n convolved with h2 of n should give me x of n. But this I know, this is only possible when h1 of n convolved with h2 of n is equal to delta of n, right? Only if this is delta of n, then I'll get back x of n. So if there is h1 of n and h2 of n such that this is possible, then we can say the LTI system is invertible. For example, if my h1 of n is given by delta of n minus n naught, so what should be my h2 of n such that this convolution gives delta of n back? So I know that I have to right shift it by n plus. So this is right shift. Then I have to left shift it by n naught to get delta of n. So my h2 of n is nothing but delta of n plus n naught, right? So this definition is nothing but it's a right shift, and this will lead to a left shift of the input signals. So when the n naught, the amount of left shift and amount of right shift are equal, I'll get back the same signal. So this h1 of n is invertible, and its inverse function is nothing but the left shift function, right? So my third property will be causality. Again, causality is also simple. I have my y of n equal to summation k equal to minus infinity to infinity h of k x of n minus k. And my y of n should depend only on x of n minus k for k greater than or equal to 0. So how can this be satisfied using h of k? Your h of k should be 0 for k less than 0 and h of k is not equal to 0, or it's not necessary, but it can be non-zero only for k greater than or equal to 0. So this is your ultimate thing for causality. So your h of k should be equal to 0 for k less than 0 to ensure the LTI system is causal. So why I state this is, even if at h of 0, if it is 0, it can still be causal, right? So if h of n is equal to 0, so let's write in terms of n only. For n less than or equal to, let's say 2, it is still causal because your y of n is depending on signals like x of n minus 2, n minus 3, n minus 4 and so on, right? Starting from n minus 3. So it is still going to be causal. It is still depending on only the past values. Okay? So that's what I mean by it can be non-zero only for k greater than or equal to 0. But necessarily for k less than 0, h of n should be, or h of k should be 0. So our final property, let us look at the stability. So stability, we have bounded input, bounded output. So if my x of n is bounded, let's say less than b, then my y of n should also be bounded. So my y of n is given by summation k equal to minus infinity to infinity h of k x of n minus k. And my mod y of n is nothing but summation, again same. And I'll have this. And this I can say it is less than or equal to summation k equal to minus infinity to infinity. I'm taking inside. So x of k h x of n minus k. Again, this is less than or equal to summation k equal to minus infinity to infinity. I'm separating this. So if x of n is bounded by b, your x of n minus k is also going to be bounded by b. So this is gonna be less than b into summation k equal to minus infinity to infinity mod h of k. Right? And for this to be less than infinity, here b is already less than infinity. So your sum of this impulse response should be less than infinity. Absolute sum should be less than infinity. So this is your condition for stability of an LTI system. So the main fact you should notice here is the entire output for any input of an LTI system can be described only using the impulse response itself. So if you know the impulse response and if you give me any input, I can tell you what the output is, right? So that is the basic idea. That is where all the things are getting simplified for linear time invariant systems, and it is very convenient for us to handle them. So now let us look at a causal LTI system described by linear constant coefficient difference equations. So in the continuous time counterpart, we would have seen differential equations. Here we have difference equations. So this is again simple. You have, it is given by this equation, described by this equation. That's a summation k equal to 0 to n ak y of n minus k is equal to summation k equal to 0 to n, or it can be any other, t equal to 0 to m, bt x of n minus t. Okay. So then how will you find y of n? So you have to do it recursively. If you can split this like k equal to 1 to n, you will have a k y of n minus k plus a0 y of n is equal to summation t equal to 0 to m bt x of n minus t. So you can write y of n is equal to 1 by a naught into summation t equal to 0 to m bt x of n minus t minus summation k equal to 1 to n a k y of n minus k. Okay. So you have to find y of n recursively from this equation. Again, to solve this, you need to have some initial conditions. Otherwise, you don't know where this y of n is starting from. Right? If it starts from infinity, you can't get the value. So you need to have some initial conditions. Is necessary to solve this. So one initial condition is called as the initial rest. So it means that before any input comes, you are assuming that your y of n is 0. So if x of n is equal to 0 for some n less than n naught, then your y of n is also 0 for n less than n naught. Okay. So we'll take an example. So let me say your difference equation is given by this. So now how will you find y of n? It is nothing but x of n plus 1 by 2 y of n minus 1. So let me take a simple example of x of n equal to delta of n. Okay. So then what will I get? So you can observe here that x of n equal to 0 for n less than 0. So your y of n is also going to be 0 for n less than 0. Initial rest condition, right? So then from y of 0, if you have to find, you will have x of 0 plus 1 by 2 y of minus 1. So this you know is 0. So this is going to be equal to 1. And what about your y of 1? It will be x of 1 plus 1 by 2 y of 0. This is 0 for you, and you will just get half because y of 0 is 1. And your y of 2 will be again x of 2 plus 1 by 2 into y of 1. So this is again 0. You will get 1 by 2 into 1 by 2. So 1 by 4. So similarly, if you see y of n, what will you get? You will get x of n plus 1 by 2 power n, right? Or 1 by 2 into y of n minus 1. But your n minus 1 will be nothing but 1 by 2 power n minus 1. Correct? So your y of n will be 1 by 2 power n. This is anyway 0. But for n less than 0, your y of n is 0. So if you have to write y of n, it will be 1 by 2 power n u of n. And since x of n was delta of n, this is nothing but your impulse response for the system. You can observe that it is going to be causal. So you can represent your causal LTI systems in form of difference equations. So we'll also see some block diagram representation. So first one you have is the summation. So if you have to add two signals, so x1 of n and x2 of n, so you will get x1 of n plus x2 of n. And the second one is, let's say, multiplying with the coefficient. So you will get ax1 of n. Okay. And if you have to get x of n minus 1 from x of n, so you just use this difference operation. So x of n minus 1. So now let's say I want to represent this system given by y of n minus half y of n minus 1. So y of n minus half y of n minus 1 equal to x of n. So this is nothing but y of n is equal to x of n plus half y of n minus 1. So how will I do it? So I have x of n and I need to add it with this signal to get y of n. So this y of n, I take it and I need to get y of n minus 1. So I use a difference operator. And then what I do? I need to multiply with this with half. So I do like this. So if they give you this block diagram, you should also be able to get back this equation, right? Okay. So in this video, we saw how easy it is to describe and analyze the LTI systems using the convolution sum. So in the next video, we'll solve some questions based on this. So until then, take care. Bye-bye. See you.